The topic of this video is atomic structures and orbitals. Some helpful knowledge I have beforehand are the basics of quantum numbers, the different shapes of orbitals, such as the s, p, d, and f orbital, the Asphadt principle, which states that electrons fill lower energy atomic orbitals before filling higher energy ones, Hund's rule, which states that each orbital is singly occupied before a double occupation, and the Pauli exclusion principle, which is two electrons in the same orbital must have opposite spins. And some things that you will hopefully learn in this video are to be able to determine and differentiate between nodal and angular nodes, calculate the ionization and ground state energy of an electron, define hydrogenic form, and calculate the probability of finding an electron in an orbital.
One orbital. So part A, we need to calculate the number of angular and radial nodes for this orbital. And part B, we need to determine the energy of this electron in EV using the hydrogenic equation. And part C, we need to find out how much energy in joules would it take to ionize the electron from this state. So for part A, the angular nodes is actually equal to the L part of the orbital. So for that, we just look at the problem and we can find that L is equal to 1. And for the radial nodes, that is equal to N minus L minus 1. So if we look at the problem, we can find that N is equal to 3 and L is equal to 1. So it's just 3 minus 1 minus 1. And that should get you 1. Alright, so for part B, we need to determine the energy of this electron in EV using the hydrogenic equation. That's this equation right here. And these are the different parts of it. So for H, it's Planck's constant, C is the speed of light, Rn is the Rydberg constant, Z is the atomic number, and N is the principal quantum number. So for hydrogen, on exams we will be given this, but for hydrogen, the EV is 13.6. So how to do this is you go in, En equals 13.6 times Z, as we see, is the atomic number. We get that from our equation over here, which is equals 4. So 4 squared over N squared, which is the principal quantum number, which we can also get from over here, which is N equals 3. So, sorry, it's supposed to be 4 squared and 3 squared. So over this, and then you should get this number. 24.2 eV. Alright, so for part C, we need to calculate how much energy in joules would it take to ionize the electron from this state. So we're given this, 1 eV equals 1.602 times 10 to the negative 19 joules. And we take the value from part B, which was negative 24.2 eV. But we take the absolute value of that. So it'd be 24.2 eV. And then you need to convert this into joules. So you take this value, 1.602 times 10 to the negative 19 times all that by 24.2 eV. And that should give you a value of 3.877 times 10 to the negative 18 joules.
Hey everyone, today we're playing Guess the Orbital. So we're given a Z of equal to 2, 3 nodes total, and negative 3.4 eV value for the first problem. We use the hydrogenic equation in this problem. En equals negative hc Rn Z squared over N squared, with H being Planck's constant, 6.26 times 10 to the negative 34th joules per second. Z equals speed of light equal to 2.998 times 10 to the 8th meters per second. RH equal to 109,677 centimeters to the negative first. Z equal to the atomic number, N being the principal quantum number, L being the angular momentum quantum number, and the number of angular nodes, and En equal to energy of the electron in the nth level. And then you have to solve for what orbital is it, and then the number of angular and radial nodes. So for part A, solving what orbital is it, I forgot to mention that there are 2 angular nodes also in this. So with an En, we use the value of negative 13.6 for hydrogen, that's assumed. So we'll set the negative 3.4 eV value equal to this equation, substituting in 4 for Z. Gives us a value of N equal to 4, which puts us in the 4th energy level. Using the 2 angular nodes, which is equal to L, we can put that in the 4D orbital. So for the second part, the number of radial nodes, we'll take the number of total nodes, which is 3, subtract the angular nodes, giving us 1 radial node. So yeah. For the second one, we're going to given 0 radial nodes, 3 angular nodes, and an EV value of negative 0.85. Again, what orbital is in, and then what are N and L, the principal quantum number and the number of angular nodes. So we'll be solving for the N and L first. So given 3 angular nodes and 0 radial nodes, the number of total nodes is L plus 1, it gives us 4. And then for the radial nodes, we're doing the radial nodes. For L, that's just 3 nodes. For the orbital, and then, we can also check our work via the energy equation. With N equal to 4. And Z equal to 1. And that we can check that against the 0.085 E value. And then this should put us in the 4F orbital. So for the third question, we were given an electron starting in the 5p orbital. It will drop to a lower orbital and emit light. And so we're looking for what orbitals are allowed according to the selection rule, which selection rule being the change in L equals plus or minus 1. So with it being in a 5p orbital, that gives us L value equal to 1 due to it being a p subshell. And this means it can either go plus 1 or minus 1 from L. So plus 1 would be value 2, so on the E orbital. And L value of negative 1 would be 0, being in the S orbital. So options for this are the 4S, 4D, C, 5S. 5S is not allowed actually. So the 4S or 4D orbitals. So for the answer to this, since the L value can either be plus or minus 1, you'd be the D or the S orbital. You can either get 4S, 3S, 2S, 1S orbitals, or the 4D and the 3D orbitals. The other rule that we have to abide by is that we have to go down in energy level, so N has to be less than 5.
Go.
Alright, I forgot to mention that it will be helpful to have a periodic table to complete these problems, but these should be the values that you should have gotten from your calculations. Since we're dealing with hydrogenic atoms, all of them should have one electron that was given. And then your Z value will just be the atomic number of each of these given atoms, so the aluminum, phosphorus, neon, magnesium, and fluorine. And then for the ground state in electrovolts, you should have gotten negative 2,296.71, negative 3,057.75, negative 1,359, negative 1,956.96, and negative 1,100.79. And then for the third energy level, you should have gotten a value of negative 255.19, negative 339.75, negative 151, negative 217.44, and negative 122.31. And that should all be in electrovolts.
Nope.
Alright, so for our next problem, we're going to be working through some examples of hydrogenic form. As we know, hydrogenic form is when an atom will have only one electron. So for this problem, I'll need you guys to just fill out this chart in reference given that the R is equal to 13.59, and that's going to be electrovolt. And then using this equation, you'll be able to calculate these N values. And then I want you to also determine the number of protons as well as electrons for each of these atoms. So for the final question, you're going to need to find the probability density of finding the electron at a distance of R equals 2 times the Bohr constant, expressed in terms of the Bohr constant, given that it is 5.29 times 10 to the negative 11 meters. All right, so after you do all of these calculations, this should be your final value. It should be 3.93 times 10 to the 28.
So hopefully by the end of this video, you have a better understanding of atomic structures and orbitals by doing calculations to find nodal and angular modes, ionization and ground state energy, hydrogenic form, and also the probability of finding an electron in an orbital. Thanks for watching.